Okay, I'm gonna record this again. Okay, this class, we're gonna talk about, again, instruction set. Okay, last class we talked about non-leaf procedure conventions. When we have a caller, we have callee. So we know the caller need to save caller registers, like temporary and argument registers, and return address, of course. And callee need to save callee registers that are those save registers, a stack pointer, a frame pointer, and the global pointer and rest. So that was something that we learned last class. But if you are non-leaf, it means non-leaf is kind of callee that is also caller. So in non-leaf, in addition to saving callee registers, we also need to save caller registers. So it means save all registers, a stack pointer, and also temporary argument and return addresses as well. So that was something that we learned before, but before going to microarchitecture and see how we can design data paths and a control unit, we still have some remaining part in ISA, instruction set architecture, that is addressing modes and also characters and strings in RISC-V. Let's see what they are about. First things that we need to talk about is about addressing. What is addressing? Addressing is the method of accessing actually operands. So when we have an instruction, this instruction has a name. This name is an operator name. There's an opcode, illustrate that, and we have some operands. Operands is what operation act on. So we address these operands with addressing modes. We have different type of addressing modes. We have immediate addressing modes for actually immediate instructions. We have, let I write it up. So we have immediate addressing to access instructions with immediate values, I-type instructions. We have register addressing for R-type instructions. We have base memory addressing or memory-based addressing. Memory-based addressing, like store type, for example. And we have another one that is more important that we're going to talk today is PC relative. PC relative addressing. PC relative addressing is a type of addressing that we compute the target, to compute the address of target or address of operands using program counter, and program counter showing which instruction is running. Program counter is that. So the branch is that type of instruction, not just branch. Any type of instruction that working with label is actually PC relative. So branch instruction has some opcode, has some sources. Branch, for example, when you said branch not equal, you are using two registers, for example, x5 and x0. If x5 is if it's not equal to x0, we go to loop. This loop is a label. that we are jumping there and want to see how we can deal with this label, okay? So we need to do addressing, and this addressing in this type of instruction is a PC relative addressing, okay? So let's see how. So we can do branch, forward branch, backward branch, so is actually forward or backward, so is sign way, you know, you can do uh, go up or down, we can add it or subtract it. So typically you can use for loop or conditions. So the fields that we have, well, let I clean this one. The fields that we have opcode, that is 7-bit. We have this function that's gonna help this opcode. We have two source registers, and the rest is immediate. But as you can see, immediate is kind of distributed around, so a split is a split. The reason that is a split because we wanted to use the regularity in our instruction. We always want to have registers in the same place to do decoding faster, okay? So if they are always same, regularity makes it faster. So in RISC computers or RISC architecture, we always want to have a similar structure for instruction. Similarity means always registers are in the same place and opcode is in the same place, same size and similar. That means makes it faster. So the immediate value is a sign extended, of course, and the addressing is a PC relative. So to compute that, we actually the target coming from program counter plus sign extended immediate multiplied by 2. We shift that to left 1 bit, so it means multiplying by 2. Why we are doing that? Because we know addresses, instruction addresses are multiples of 2. In this computer is actually multiples of 4. So it means the addresses of instructions have 2 bits of 0 or 1 bit of 0. The least significant bit is always 0, the address, because they are multiples of 2 or multiples of 4. So if we actually shift them to right, because those 0, it doesn't have any value, so we can shift them to right when we want to make this immediate address, and this is going to give us opportunity to jump more, you know, to bring have a broader jumping space. Okay, so this is the reason. So let's do that with the example. Imagine we have this code, we have a loop and one instruction like add immediate x5 minus 1, and we have another instruction branch not equal x5 and x0 loop. Imagine we know the address for loop is 1000, and address for branch not equal is 1012. Okay, that's the address. Okay, we know this address. So we know these addresses. Imagine these addresses are just decimal numbers. We don't want to make it complex. So we want to see how we can compute encoded immediate value. What is this immediate value? Immediate value. Okay. So to computer to find immediate value, actually assembler compute this immediate value based off that. First, find offset, and offset coming from the address that we are jumping, that is 1000, minus the address that we are is 1012, that is minus 12, and then immediate value is minus 12 divided by 2, minus 6. We divide it by 2 to do compression. We do compression. So we are compressing that. We are just using that extra bit that we have. Why we are dividing by 2 but not 4? Because instructions are 4 bytes, not 2 bytes. The reason is that we want to be, because we have two type of RISC-V, RV64C and RV32C. In here, this is instruction 16 bits, instruction here is 32 bits. Because we want to be compatible with both of them, we divide by 2. We don't divide by 4, okay? But in RISC-64, that we are mostly work with that, you can even divide by 4. We divide by 4, we are expanding the range of actually jumping area. That's very good. Okay, so we learn why we're dividing by 4. When we divide here by 4, here we to find the target, we need to multiply by 2 or by 4. Anyway, okay, that was something that I wanted to mention. So generally, branch is a PC relative. Another PC relative instruction is jump and link. Jump and link also using label. Remember, we can do like jump and link x1 a factorial that we use in last class, factorial function. So this is the label. So in this label, you still can use PC relative addressing for jump and link, but in addition to jump and link, doing another things. If you remember that, we also saving a return address. So we always saving return address as well. So we save return address before jumping. So that was something that we need to consider. So we do return destination is equal to program counter plus 4, and then we do PC relative. A new PC relative, this is the old one, is PC relative old plus immediate value that is shifted by 1, shifted to left. This is here, we multiply by 2. Okay, when we shift to left, we multiply by 2. When we shift to right, we divide by 2. Okay, but this give us range of jumping because this is 20 bits, so it give us plus minus 1 megabyte range. The other one was just 4 kilobyte because it was just 12 byte. It was just 12 bits, sorry. It was 4 kilobyte, and here you have 1 megabyte. It still is more, but it's still, we are not enough because this computer can address 4 gigabyte memory. So we need to kind of address data space too. We're going to see that how. So that's a jump and link. So this is the J type. So we do, this is kind of immediate bit. Again, is a split. Well, let's clean this up. Again, this is split. We have 7 bits opcode. Register data using 5 bits, and the rest are immediate. 20 bits immediate, and the addressing is still is PC relative. Okay, and this is called actually absolute jumps. This kind of jumps called oh, sorry, not this one. Okay, so that was PC relative addressing. So PC relative addressing give us to opportunity to jump around like 20 bits, not more, and 20 bits like 1 megabyte plus minus 1 megabyte. Okay, but if we want to do more, what we can do a trick that's called absolute jump. In absolute jump, we are using two instructions and jump and link return to do jump. Okay, remember in jump and link return, what happening? In jump and link return, we are finding register's destination, that is program counter plus 4, whatever program counter is this, we plus it by, we add it by 4 and put it in register data. This is first thing, and then we jump. But when we want to jump, this is not PC relative anymore. This is register addressing instructions. So the new program counter is a register source sorry, plus offset. So for example, here is X, I put register source and offset, and oh, sorry, register destination. This is register destination. This is register source. So we have one register source that we add that with offset, and that's a new program counter. And we also put the return address, program counter plus 4, in this register data. Most of the time, if you remember, if you want to use that as a return, we put jump and link return x0, because we don't want to save that. X0 is always 0, and offset, it can be any number, like we can put 0, and rs is, for example, stack pointer, like x2, that we always use that to jump, for example, and return to, for example, this address or whatever that is in a stack, for example. Okay, so how we can use jump and link to jump more than 1 megabyte? We can use this instruction and use a trick. What about we use a load upper instruction? We have an instruction called load upper immediate. Load upper immediate has 20 bits immediate value. You can put 20-bit value here and put it in a register X5 and use this dynamic jumping. This is a dynamic jumping. Do this dynamic jumping. You use 20 bits in X5 and another offset that can be 12 bits in this lower part, and in addition, because this jump and link doing adding here, doing register based addressing, you do add offset with this, and the overall gonna be 32 bits. So with 32 bits, you can have 2 power 32 address. So it means 4 gigabyte. Gig is 2 power 30. So 4 gigabyte is the size of the memory that this RISC-V is supporting. So with this trick, we can address all the memory, and that's amazing. So that's called absolute jump. Maybe you ask me, oh, okay, we use 2 instructions, so this makes it slow. No, it doesn't make it slow. The reason is that we don't want not most of instructions using this, and we talk about that. If most of instructions are fast, but very limited of them are slow, nothing change. It's not change the performance of the old CPU. Okay. So there is example. So imagine we have a program that need transfer control with different target address. We know that if we use branch equal, we can jump 4 kilobyte. If is jump and link, we can do 1 megabyte up and down. And if we do load upper immediate and jump and link return, we can go to 32 bit or 4 gigabyte addressing. So the question is, you need to jump to a function located in 2 megabyte away from program counter. Which kind of instruction you can use? Because this is 2 megabyte is more than 4 kilobyte and 1 megabyte. So we need to use C. So the C is the proper answer. The next part of the class, we're gonna talk about some character data. As we know in computer, we also, in addition to numbers, we use characters. In digital logic, we learned that characters are also like numbers. Like, for example, we use 7 numbers for 7 digits for one character, like A, for example, whatever. It's not exactly, I just wrote it, but this called ASCII. ASCII is a coding. ASCII is a coding that we use 7 bits for characters. So we already have that. I'm gonna just review that. You had that in digital logic class. So with these 7 bits, you can have 128 characters. Mostly 95 is printable characters, and 33 is not. They are not printable. They are control characters. Mainly English and digits can go there, and some symbols. But this is good for English. If you use other languages like Latin language or European language, you need more. That's why we have another coding called Latin 1 that use 256 bits, that you can have 8 bits, sorry, that you can have 256 characters. In this case, you can have some European languages as well, like these specific characters. But that wasn't still enough for new computers, like a graphical operating system like a Windows or Java, for example, or if you want to support more languages or more alphabet, you need, or symbols, you need to have more. We have different type of Unicode. Unicode 8, 16, and 32, that right now 32 is something that, for example, Windows using, and it can have 2 power 32 characters. You can have all languages and every characters and emojis and so many other things. So the idea is the ASCII is small, but Unicode is actually global standard and used. You can see here the ASCII code. As you can see, lower than 32 are the control characters. They are not printable. Between 32 to actually, between 48 to 57 are the numbers. Between 65 to 90 are capital alphabet, and between 97 to 122 are lowercase. As you can see, there is relationship between this and this. You just need to add them with something to change the characters from capital letters to lowercase. We had that example in digital logic, I think. Anyway, that's how we can put characters in computer. We just need to use same way. It's binary, but you need to use multiple binary values like 7, 16, or 8 to illustrate each character. But we also need to have some instructions to work with byte or half-word or double word. Byte is 8 bits, half-word is 16 bits, and word is 32 bits, and double word is 64, so we didn't write that. So we have some instructions to access memory but with byte halfword. And so we have load instruction. Load instruction, if you remember, we use load instruction to access memory. So we find the address. Uh, uh, so this is the memory based addressing. So in memory-based addressing, we are doing this register source. The address is in the register. We add that with offset, and then put the value of that. So that's the address of that, and the value of this. We read this value and put the value in register destination. So in this case, if we use load byte, we're gonna just take 1 byte because the memory is a byte addressable. If we use halfword, we're gonna have 2 bytes from there and put it in register destination. Register destination is 8 bytes anyway. You have enough space, and you can fill the rest with 0 or sign. If you do this instruction, it's going to fill them with sign extended. We also have 0 extended. In 0 extended, we have load byte unsigned, load half word unsigned, load word unsigned. The rest is equal, same as before. We just do addressing using memory based addressing. For a store, we just have one type, and in a store, we are storing to the memory, into the memory. So we find the same way, addressing is the same way for the memory. And what we are doing register source. We are put that in a memory that the address coming from offset plus this address of RS1. So the address of register 1, not the number of register 1, the address that is there, we add that, the value of that, maybe I write value is value of register sort 1. We add them with offset and get the memory, take the address, put the address, and write in that address this register. Okay, register 2. So in this register 2 is actually 8 bytes. In if we do a store byte, just gonna do a store byte. This is for a store byte. If we do a store half, we're gonna save this part. And if we do a store word, we do just 32 bits. And if we do a store D or a store double word, it's going to be 64. Okay, so this is how we access to memory in a different size: byte, half word, word, or double word. Let's do this example. This is example of a string copy. A string copy or a str copy exists in C++, but we wrote in here this as a function, and we want to write this function with assembly RISC-V. We have 2 arguments, x and y, and what we are doing, we have the counter variable, that this variable is counting, that start from 0, and then we do a loop, and inside the loop we are copying and checking if we are at end of a string. Strings in C++ has finished with \0. So whatever is there, like A, B, C, D, E, F is a string, but it's finished with \0. That's a difference between character um, array and a string. In a string, we are finishing with \0. Anyway, and we are doing this code. This while loop is repeating and copying everything. So we want to write that using RISC-V assembly code. We need to know a couple of things. First of all, we have three values that we need to know. The counter value I is in x19, but x19 is a little tricky because x19 belongs to save registers. Is actually S3, save register S3. So it means if it's S3, callee need to save that, preserve that using stack. X11 is actually X10 and X11 are argument registers. A0 and A1 argument registers. So we don't need to worry about that. I mean, the callee, that is this function, strcopy is a callee, doesn't need to worry about that. Okay, so we just need to consider this too. So x11 is a base for x and x10 is base for y. Okay, let's see how we can write this code. Because we are using one save registers, we need to preserve that. So we have at the beginning of procedure, this is the procedure. In the first of procedure, we are actually allocate memory, allocate stack. We allocate the stack. How much? Allocate the stack because it's just one register is 8 byte. We allocate the stack and we put we store x19, that is one of the save registers there, and then we put it 0. We made it 0. Okay, and when we are finishing, we do the same back. We are storing, we load the value that we put in a stack in x19. We restore x19 back, and we pop, and then we jump return to caller. That probably is a main function, whatever. Okay. Okay, so that was regular, nothing more. Let's see what's happening inside this. So inside this, you need to know two things. You have two arrays, array y and array x. And this array y, we are copying y to x. Okay, we are copying this to this. Okay, we have some information. First of all, the base of this is x10, base of this is x11. Okay, we need two more registers. We need two more registers to actually count these values. We don't want to change x10 or x11, and we need to use another kind of pointer to point this array for, let's see what's happening here. What we are doing, we use a pointer called x5 to point different characters in x10. As you can see here, we are adding x19, that is a counter, with x10, that is a base address, and add that to x5, and x5 is the address of y0. and then we read it, we put the value, so we have another registers called R6 that the value stay there. Value stay there. So we read this, we put value here, and right now we have this value. So we also have another pointer is here x actually 7 to point different characters in x array. So we add that by x19, that is a counter, and we save x6 over there. The x6 was here, we save that in this and do one by one and add x19 to 1, but we always check it out if we got to 0. If x6 becomes 0, if it's not 0, we are keep going. If it's 0, we jump to L2, and L2 is just finishing and popping. So that's how we can do string copy. This example was a very good example because at the same time, you can work with procedure. You can use allocating memory and deallocating memory, stack, and do a loop. Okay. Here we have a summary of this addressing mode. As I explained, we have 4 different addressing modes in RISC-V. We have immediate addressing. When we have immediate value, it's just a 12-bit value. We have a register addressing that we just have registers. That registers are 5 bits because we have 32 registers. We have base addressing. In base addressing, we can access. We are actually using offset plus register value of register to find a new address to go. And as we explained, you can have a double word, half-word, and byte to load or restore. And we also learn PC relative, that is for instructions that use label. In this case, you can have actually a 20-bit jumping, that is give you actually plus or minus 1 megabyte addressing. We can do a trick to do PC relative to make it jump more. That we saw that using combination of actually load, upper immediate, and branch and jump, branch and link return. Okay, and the last part is just a summary of all of this encoding different type of instruction, register type, immediate type, store type, store and branch type, and different jump. Okay. Next class we're going to talk about processor design and ILU. Have a good day.